Okay, so now we're going to start with chapter 6, which deals with the topic of thermochemistry. We're going to define thermochemistry shortly, but before we do that, let's talk about energy, the concept of energy. What is energy? Well, energy is basically the capacity to do work, which begs the question, what is work? And work is basically the ability to move an object a distance by applying a force. All right, so if you apply force to an object and the object moves, then work is said to be done. Now, there are two types of energy. You have potential energy, which is the energy an object has by virtue of its composition or position, and kinetic energy, which is the energy an object has by virtue of its motion. So anything that is moving has kinetic energy. Now, there are formulas that we can use to calculate potential and kinetic energy, keeping in mind, as we said before, that potential energy is the energy an object has by virtue of its position. And in this context, when it's talking about the position of an object, it's talking about it in reference to a gravitational field. All right, so in the context of the Earth, for example, the potential energy can be measured according to the distance from the surface of the Earth, and it is given by this formula. Potential energy is equal to mass of the object. So the object could be a ball or a sphere or any object times g. Now g is a constant, which is known as the acceleration due to gravity. We met this before. It has a value of 9.8 meters per second squared. And h is the height of the object above the Earth, right? So if you plug those numbers into this equation, then you get the value for the potential energy. Let me just say that if the mass is in kilograms, the acceleration due to gravity is in meters per second squared, and the height is in meters, then the unit of potential energy is going to be joules. Now, in the case of kinetic energy, as we said before, that's the energy an object has by virtue of its motion. And this is the formula that we use to calculate it. The kinetic energy is equal to half mv squared, where the mass is in kilograms, and v would be the velocity in meters per second. So if you plug in these values or these units, again, the kinetic energy unit would be in joules. In fact, the joule unit is the same thing as this collection of units right here, kilograms, meter squared, seconds to the minus 2. And that is true, of course, in both cases based on these equations. All right? Now, as I said before, work is said to be done when an object is pushed a distance or pulled a distance. And as you can see here, the definition of work is the product of the force times the distance moved when the force is applied to an object. So this is the equation we can use to calculate work. The unit of force would be newtons in this case, and the unit of distance would be meters. And again, the unit of work would be the same as the unit of energy, actually, which would be joules. All right. Now, when it comes to real world collisions, what you'll find is that the collisions are not perfectly elastic, which basically means that the energy is not totally transferred from one object to the other. Some energy might be converted to sound energy or to heat energy, but the kinetic energy is not totally transferred when two objects collide. And one can see that, for example, when a ball, like a tennis ball, is held up above the ground and then released, and it falls, and we all know what happens. It bounces, right, hit the ground and then bounces, but of course it does not go up to the same height as the original height from which it is released. And that's because some of the energy that is transferred from the ball is transferred to the ground in the form of heat or whatever, and therefore the ball loses energy, so that when it gains some potential energy up here, the potential energy here is not the same as the potential energy when you first release it, because some of the energy has been transferred when it collided with the ground, and that energy is lost consecutively with each bounce. All right. So that's one thing that you must recognize in the real world. Collisions are not perfectly elastic because the kinetic energy is not totally transferred. So energy transfer occurs as a result of inelastic collisions in the real world. Okay, so let's talk about thermochemistry. So that's what this chapter is all about. Thermochemistry is a study of energy changes that occur during a chemical reaction. And in this context, we have to familiarize ourselves with certain terms. One would be the system. Now, whenever we talk about a system in science, we're talking about the part of the universe that we are interested in terms of the changes that it undergoes, etc. So a system could be a test tube, it could be a beaker, it could be a nuclear reactor, it could be anything, right? So we call that a system. The universe, well, the system is part of the universe. So therefore, once we identify what the system is, the rest of the universe is simply called the surroundings, right? So one could say, and I've seen this expressed in a sort of mathematical equation, that the system plus the surroundings is equal to the universe. Okay, so there are actually three types of systems that one can study. So all systems that we can look at fall into one of these three categories. You can have an open system where you have basically the free flow of energy and matter between the system and the surroundings. You can have a closed system, and in this system you can have energy flowing into and out of the system, but matter is not flowing into or out of the system. So as far as the matter is concerned, you either have the matter located in the system, cannot get out, or if you have matter outside, it cannot get into the system. But energy can get into the system as well as leave the system in a closed system. And then the third category is known as an isolated system, and in this case, neither matter nor energy can flow through the walls of the container in this system. All right? So these are basically the three types of systems. Now, let's talk about another term, internal energy, which is the total energy that is contained within the system. Part of it would be kinetic energy, and the other part is potential energy. Now, as far as the kinetic portion is concerned, there are actually three types of kinetic energy. You have the kinetic energy, which comes about as a result of translational motion. You have another type of kinetic energy that comes about as a result of rotational motion. And then the third type is vibrational motion. Now, in the case of translational motion, what that means basically is that the particles, molecules, whatever, will be moving in straight lines, only deviated from the straight line direction if they're hitting other molecules or hitting the walls of the container. Rotational motion, as the name suggests, involves or implies the molecule rotating around a certain axis. And then vibrational motion is where you have, for example, if you have a molecule, if you think about of a molecule as being two objects connected by a spring, you know, the sort of vibrational behavior that a spring displays is basically what we're talking about here when it comes to vibrational motion. So these are the three types of kinetic energy or motions that would result in particles having kinetic energy. Now, when it comes to potential energy at this microscopic level, there are two types. You have what are known as intramolecular forces, which are the forces that exist within a molecule. So, for example, if you have two atoms connected to each other by a covalent bond, which is basically a shared pair of electrons, then you're going to have forces of attraction between the positive nuclei of the atoms and the negative electrons that are shared between the atoms. Or you can have intermolecular forces, which, as the name suggests, are forces that exist between molecules. Later on in this course, we'll talk about the different forces of this type. You have dipole-dipole interactions, van der Waals forces. Those are the main two types. There's also a special type known as hydrogen bonding, which we'll discuss later on. So those would fall collectively under the category of intermolecular forces. Okay, another term that I need to talk about is heat, which is symbolized by the letter Q. Heat is basically the energy transfer resulting from thermal differences between the system and surroundings, all right? And what happens always is that if you have two objects that are physically connected to each other, and one is at a higher temperature compared to the other, then the heat flow will naturally occur spontaneously from the higher temperature object to the cooler temperature object, right? You'll never have the heat flowing in the opposite direction. That will become important in certain problem solving exercises in your upcoming assignment. Okay, so as I said before, if you have two objects connected to each other, then if one is hotter than the other, then the heat flow will go from the hotter object to the cooler object. And I should say that that heat flow will continue until both objects are at the same temperature. In other words, both objects are at a state of what is known as thermal equilibrium. All right? So that's what happens all the time, right? When it comes to the flow of heat, it always goes from the hotter object to the cooler object. Now, this diagram here is an explanation of what we just described. So let's say we have two gases in contact with each other. Well, actually separated by a hypothetical thin wall. Now, if you remember from the previous chapter, we talked about the fact that the kinetic energy displayed by particles of gas is proportional to the temperature, right? So the hotter the object, the greater the average kinetic energy of the gas particles. So what is being shown here is that you have argon separated to the left, and its energy is higher compared to the nitrogen molecules on the right of the hypothetical thin wall. So when the argon atoms bounce against the wall, the energy is picked up by the nitrogen molecules, right? So that is basically the reason why you have the heat flow from the hotter object to the cooler object. What is actually happening is that you have basically kinetic energy being transferred from the hotter object particles because they're more energetic to the cooler object particles because they're less energetic. And it is this sort of inelastic molecular collisions, as indicated in this diagram, which is responsible for the transfer of heat. All right? Okay, let's say some things about work. Work can be considered to be an energy transfer between system and surroundings. All right. Now, if you recall from the Prevailing equation, PV is equal to nRT. The product PV can actually be seen as an energy term. All right. So if you think about a gas undergoing either compression or expansion, we can actually calculate or express the energy changes involved in terms of the pressure and the volume changes that are taking place. So if you're talking about compression, right, in other words, you're going from the diagram on the left to the diagram on the right. All right, compression of course involves reducing the volume of the gas, which means that work would have to be done on the gas in order to achieve this. All right, so that's what is happening going in that direction. Going in the other direction, if the gas is expanding, then what that means is that the gas is actually doing work against the surroundings. So going into the compression direction, the surroundings will be doing work against the gas, while going in the other direction, the gas is doing work against the surroundings. So we're going to look at the equations that we can derive based on those observations. So this is how we calculate the work that is done. This is the equation. Work is equal to minus P times delta V. Now, I'm not sure if you're familiar with the symbol delta from your math courses, but delta literally means change of. So we can read delta V meaning change of V or change in V. And the change in V would be always going to be the final volume minus the initial volume. The final volume minus the initial volume. So maybe I should add something here. Let me write this here. Whoops. Okay, let me erase that line. Go back to pen. So let me just write here that delta V is equal to V2, which is the final volume, minus V1, which is the initial volume. All right. So the sign of delta V, of course, will influence the sign of W. All right. But it's very important to understand and interpret correctly what the sign of W actually means. All right. First thing you need to think of and take into consideration is the fact that we're talking about work from the perspective of the system. So in other words, you kind of like to have to imagine you being the system, right? And taking the view of the system in terms of whether or not you experience an increase in energy or decrease in energy as a result of the changes in work. Now, as stated here, if work is done by the system, let me get back to the pointer mode. Okay, if work is done by the system, that means that the sign that's associated with that work would be negative, right? Because when work is done by the system loses energy, right? And therefore, the value of that work would be negative, all right? Now, let me just go back here and say also that if work is done by the system, that corresponds to an increase in volume. Hold on, let me make sure I'm saying the right thing. If work is done by the system. Okay, yeah, so that corresponds to an increase in volume, which means that V2 will be greater than V1. If V2 is greater than V1, that means that delta V will be positive, and therefore if you plug that value here into this equation, work will become negative, all right? So that's what happens when work is done by the system. And of course, the opposite is true when work is done on the system. So this is what I was referring to. If you're going from here to here, right, where the system is expanding, that means that V1 or V final will be greater than V initial, and therefore work would be negative. Now, on the other hand, if work is done on a system by the surrounding, that means that the sign associated with work would be positive. And if that's the case, that corresponds to the opposite direction here, where compression is taking place. If compression is taking place, right, that means that delta V would be negative because the volume would be reduced. And if you plug that value of delta V into the equation I showed you before, that means that work will be positive, and therefore the system will gain energy as a result. Okay, so that's as far as work is concerned. Now, here's another term I need to introduce to you. States of a system. When we're talking about the state of a system, we're talking about, or we're referring to its exact condition as determined by different factors, including the kinds and amounts of matter present, the structure of this matter at the molecular level, and the prevailing pressure and temperature. All right? So, and let me just try to clarify something here, because I'm quite sure before this, in your introductory chemistry or high school chemistry, you learned about the states of matter, right? Solid, liquid, and gas, right? Well, that is true, but that is not encompassing the actual definition of what a state is. You can have different states even within the same phase. So, for example, let me use an example using copper metal. So let me go back to the pen mode here. All right, so let me scribble something up here. Now, if you have, for example, copper at 50 degrees Celsius, and you heat it to copper at 100 degrees Celsius. Now, the copper here would still be a solid, and the copper here would be a solid as well. But because the temperature changes from 50 degrees to 100 degrees, we're talking about a change in state, right? In other words, the copper at 100 degrees Celsius would be of a different state compared to copper at 50 degrees Celsius, all right? So that's what we mean by its state, right? If the temperature changes for a substance, even if it doesn't melt or convert into a gas, there's still a change in state. Here's another example. If I have hydrogen gas at 1 atmosphere and I change the pressure so that you end up with hydrogen gas at let's say 1.5 atmospheres, that is also a change in state, simply because the pressure has changed from 1 to 1.5 atmospheres. All right? So I hope this clarifies what we mean by a state of a system. Basically, the state is describing the condition of that system based on the different factors as listed here in the definition. The kinds and amount of matter present, the structure of this matter at the molecular level, and the prevailing pressure and temperature. Let me give you just one more example. And that's in reference to changes at the molecular level. There are, well, more than one forms of carbon, but I'm just going to mention carbon, which can exist as graphite, and you have carbon, which exists as diamond. Again, these are two different states simply because the arrangement of the atoms in graphite is different from the arrangement of the atoms in diamond. All right, so that's basically what we mean by a change of state, and we can determine the internal energy that accompanies a change of state, and that would be given by this equation. Let me write it here. I think I have it further into the slides, but it doesn't hurt to express it here. The change in energy, internal energy, would be equal to the final internal energy minus the initial. All right, and the internal energy is what we call a state function. It's a function of the state of the system. So that brings us to state functions. And here's a definition of a state function. It is a property that is of a unique value that depends only on the present state and not on how the state was reached, nor on the history of the state. All right? So the change in state energy, or I should say internal energy, that's a state function. It depends on the initial and final states. And here we have basically an analogy that is used to explain this. So the base of the mountain here would be representing the initial state. The peak would represent the final state. And it doesn't matter if one person take this journey labeled A or this journey labeled P, or I should say B, to go from state 1 to state 2. The elevation gain would still be the same. All right? So the elevation gain would basically be analogous to the state function delta U. Okay, so delta U, doesn't matter how you get from the initial to the final state, delta U would be equal to the difference between those two values. All right? Okay, so let's talk about now the first law of thermodynamics. The first law of thermodynamics, which says that in any physical or chemical change, energy can be exchanged between a system and its surroundings, but no energy can be created or destroyed. That law is also known as the law of conservation of energy, and it can be expressed in terms of a relationship between the change in internal energy, the heat change that takes place, and the work that is taking place as well. So the first law can be expressed mathematically as delta U, the change in internal energy, which is equal to Q plus W. Q is the amount of heat change and W is the amount of work. Now, it's very important that you understand the meaning of the signs associated with Q and W. All right? Now, as you can see here, it says that whenever you have a situation where energy is entering a system, in other words, if delta U, if the energy is positive, that will happen under two circumstances. One, if Q is positive. In other words, if heat is absorbed by the system. The other is if work is done on the system, in which case W is positive. All right? So those are two ways that energy can enter into the system. And of course, in the case of energy leaving a system, then that can be done in one of two ways. One, if heat is given off, in which case Q is negative. And two, if work is done by the system, in which case W is negative. So this diagram below basically summarizes what I just said. These are the two ways that energy can enter into the system: by the addition of heat or work done on the system, or in terms of energy leaving the system, heat loss or work being done by the system. All right? Now, let's talk about heats of reaction. The heat of reaction, Q reaction, is the amount of heat that is exchanged between the system and its surrounding. Now, in the case of exothermic reactions, right, In the case of exothermic reactions, by definition, what that means basically is that heat is given off. And that will take place in a non-isolated system. Heat is given off to the surroundings, and therefore Q is negative. In isolated system, heat is given off, and as a result, the temperature will increase. All right. Now, in non-isolated system, temperature will also increase, but the rate or the extent of increase would not be as high. We're going to see that in the next couple of slides. In endothermic reactions, the opposite will be true. Heat is absorbed by the system, which means that Q will be positive, right? Now, in isolated system, that would correspond to a fall in temperature. And again, a fall in temperature will occur in non-isolated systems, but the extent of the fall would not be as great as in the case of isolated systems. Okay, and to explain this further, we're going to look at an example of an exothermic situation, an exothermic reaction. Now, here we have three possibilities. The first of which is virtually impossible. It's purely hypothetical. Just displayed here just to make a point. If you have a vessel that basically will allow for all the heat to be generated in an exothermic reaction to escape to the atmosphere, then basically what will happen is that the temperature of that resulting product will be the same as the temperature of the surroundings, right? Now, that is virtually impossible because there's virtually no vessel that will not absorb some of the heat, all right? There's no system that will not absorb some of the heat that is generated. In fact, more often, you'll have a situation as shown here in the middle container right here, where again we have an exothermic reaction, but some of the heat is absorbed by the resulting mixture, and therefore the temperature of that mixture will rise. The rest of the heat will simply escape into the surroundings, all right? Then we have a situation here which consists of an isolated system. In this case, we're using styrofoam cups. Styrofoam is a very insulating material and therefore will not allow for any heat to escape. So therefore, basically after the heat is generated, the heat would cause the temperature of the resulting mixture here to rise, all right? And the extent of the rise in temperature will be greater compared to this situation right here. As you can see, the temperature here is 35.4 as opposed to 32.2 previously in this system, all right? So this is what happens in the case of an exothermic reaction. And if you compare that to an endothermic reaction, in fact, you should be able to figure out what happens in an endothermic reaction. The temperature will remain the same here. The temperature would fall in the case of this one here. And here you'll have a temperature falling to a greater extent, all right? So that's basically what happens in an endothermic reaction. Okay, now let's do some algebra with what we have just learned. So far, we have been introduced to two equations. The one for work, which deals with a gas trapped in a vessel, and the conservation of energy law, the first law of thermodynamics, delta U is equal to Q plus W. Now, let's look at a situation where we have a change taking place where heat is produced, but there's no change in volume. So the volume is constant. So if delta V is equal to 0, right, that means that W is equal to 0. And if W is equal to 0, that means that this 0 here would, this W would disappear, and therefore delta U would be equal to Q. So we can write that as delta U is equal to QV. This V basically means that the volume is held constant. So what this means in this situation where the volume is held constant is that all the thermal energy that is produced by conversion of chemical energy will be released as heat, all right? And therefore, basically no work would be done by the system because the only change in internal energy is in the form of heat that is produced. So we're assuming, of course, that this is an exothermic process because heat is produced. Okay, so therefore delta U would be equal to QV, and both of them would be negative. Okay, now what happens if pressure is constant? If the pressure is constant, then we substitute minus P delta V where W is. We end up with this equation, and we can rearrange it to get QP is equal to delta U plus P delta V. All right, and what that tells us is that if heat is lost, which is a form of QP, QP is the heat lost, then that would correspond to some change in the internal energy and some change in the volume. So basically, there'll be some expansion of the work of the gas as it works against the surroundings, and there'll also be a change in internal energy of the system. All right. Now, compared to the previous diagram where the volume was constant, the amount of heat liberated would of course be less. All right. Okay. Now, let's talk about enthalpy, another term. Enthalpy is basically what we just discussed. Heat change taking place under conditions of constant pressure. All right. And the formula that we were exposed to, or that we derived, QP, that is basically the same thing as a change in enthalpy. So we can replace QP with delta H, and that would be equal to delta U plus P delta V. So here's a definition of enthalpy. Enthalpy is the sum of the internal energy plus the pressure volume product of a system. Couple of things about enthalpy. It's an extensive property, which means that it depends on how much substance is present in a system, and it is also a state function. And the reason why enthalpy is a state function is because U, P, and V are all state functions. All right. So how do we use delta H? Well, firstly, let me say this. Delta H can only be measured experimentally. Negative values indicate that the reaction is exothermic. In other words, it produces heat. And positive values indicate that the reaction is endothermic. In other words, heat is absorbed in those reactions. And therefore, if you think about it, if you do a cyclical observation, in other words, if you start with a reactant in a reaction and it forms a product, and then the product goes back to the reactants, then the total enthalpy change of that process will be zero. All right? And for problem solving purposes, one can view heat change being absorbed as an endothermic in an endothermic reaction as a reactant. So we're going to see some examples of this later on. Basically what this is saying is that in an endothermic reaction, delta H, or the heat change, can be seen as a reactant, and in an exothermic reaction we can treat it as a product like any other chemical for the purposes of calculations. But we're going to talk about that later on. This diagram basically shows you the essential difference between an exothermic and endothermic reaction. In an exothermic reaction, as you go from reactants to product, heat is lost. So therefore, the enthalpy of the products will be less than the enthalpy of the reactants, and therefore delta H would be negative. In the case of endothermic reaction, the enthalpy of the products would be greater than the enthalpy of the reactants, so delta H would be positive in that case. All right, let me see what next. Okay, let's talk about calorimetry. This is basically an experimental technique that is used to measure heat flow in chemical reactions. And you have different types of calorimeter or calorimeters. The one that you see here on the screen is the very low-tech version, consisting of 2 styrofoam cups. You have a stopper here, or cork, or a cover, which covers whatever is inside the cups. You also have a thermometer, which is used to measure the temperature changes, and this rod here is basically a stirrer to ensure that you have a mixing of the reactants inside the cup. And the calorimeter is what this is called. All right. So calorimetry, the type of calculations involved, is based on the law of conservation of energy that we talked about earlier. Now, some other definitions I have to point out to you. This one is called the heat capacity, which is the amount of heat required to change the temperature of a system by 1 degree Celsius. In some textbook, you might see 1 Kelvin. It's the same thing. Same thing numerically. So it doesn't matter if the temperature change is in Celsius or Kelvin. The heat capacity will be the same numerically. And we can calculate the heat capacity by using this equation. C is equal to Q divided by delta T. And of course, the units of C, the heat capacity, would be joules per degree Celsius or joules per Kelvin. Now, another term is a specific heat. which is the heat capacity of 1 gram of a sample. And in that case, the specific heat, which, by the way, the symbol for specific heat is lowercase c. Let me put that here. So, okay, what's going on? So specific heat would be lowercase c, to distinguish between that and uppercase C, which is the heat capacity, right? So basically, to get lowercase c, we divide the heat capacity by the mass. And remember, C is equal to Q over delta T. So if we plug in this expression where C is, we end up with this relationship, right? C, lowercase c, specific heat is equal to Q, the amount of heat, divided by mass in grams times delta T, the change in temperature. And the units of specific heat are given here: joules per gram per degree Celsius, or joules per gram per Kelvin. Okay, and well, honestly, you won't be using this. I'll just mention this: the molar heat capacity, which is basically the same thing as heat capacity, excepting on a molar basis. It is the product of the specific heat times the molar mass of a substance, and that's it. Now, the useful form of the equation for specific heat is Q is equal to M times C times delta T. And I'm just seeing here that this C here should be a lowercase c. So please make a note of that. So this should be Q is equal to M times lowercase c times delta T. So based on this equation, one can clearly see that if delta T is positive, in other words, if there's an increase in temperature, that means Q would be positive. And as a result, we can conclude that heat is gained by the system, which makes sense. If you put heat into the system, there will be a corresponding temperature increase. Conversely, if delta T is negative, right, if delta T here is negative, that means M, or I should say Q, will be negative, and that corresponds to a heat loss by the system, which again makes sense. If heat is lost by the system, there will be a decrease in the temperature. And what you see here is basically a list of different substances and their specific heat. What you need to realize that specific heat is a physical property like density, like melting points, boiling points, refractive indices, and so on. All right, so it's one of those things we can use to identify a substance. And you can see here that typically metals tend to have relatively low specific heats. Water has the highest specific heat of these substances, and that is due to a phenomenon known as hydrogen bonding, which we will talk about later on. Okay, so we're going to stop here. Make sure that you complete the assignments, which will be available online. And that's it. Okay, until next time.